All right, we'll discuss the topic of matrix inverses. Probably the most important question we can ask about a given matrix is whether or not it has an inverse. So if we know that a matrix A has an inverse, then the following is true. This will be for a square matrix. So for a square matrix A, its inverse on the left is the same as its inverse on the right. Now if A is not square, it may have either a left inverse or a right inverse, but clearly it can't have both, because if A is m by n and m is not equal to n, then the multiplication on one side won't be the if the multiplication on one side is legal, the multiplication on the other side may not be legal. Okay, so matrices with inverses are called invertible, or non-singular. If a matrix does not have an inverse, we say it's non-invertible or singular. So let's look at an example of a singular matrix. So this is a singular matrix, and we can say, okay, why is this matrix singular? That is, why does it not have an inverse? If we look at geometrically what this matrix looks like, plotting the columns here, we have 1, 3, this point, and 2, 6, this point, so if we were to multiply this matrix A by some other matrix, the columns are combinations of the columns of the result would be columns of combinations of the columns of A. And since both these columns lie on the same line, the combinations will also lie on that same line, right? So this line, we have a line that goes through the origin that passes through both of these points. And so anytime we multiply another matrix by this matrix A, the result will also lie on this line. And so therefore there's no way that we can get the column 1, 0. So we can easily see that geometrically there's no way that we're going to be able to find an inverse for this matrix. Another reason that we can see why this matrix is inverse, so let me just write Okay, so that's one way that we can see that this matrix is invertible. Another reason, another way that we can see it if I can find a non-zero solution to the equation ax equals 0, then the matrix has no inverse. It's singular. So in this case, we can find that if x equals 3, negative 1, that solves this equation, ax equals 0. Now we can say, okay, why does that work? Why is it that if there's a solution, a non-zero solution to ax equals 0, the matrix is not invertible? Well, suppose A did have an inverse. Then we could write A inverse A x equals A times the 0 vector. This gives the solution x is equal to 0. So this is proof by contradiction. In other words, if A is not equal to 0, but there's a solution to ax equals 0, then the inverse can't exist. Okay, so we know a little bit about geometrically when can the inverse exist, just a little bit, and we know a little bit about if there's a solution to ax equals 0, this implies that there is no inverse. Let's talk a little bit about finding the inverse. So suppose I have a matrix A, and I want to find its inverse. So in this case, we want to find the matrix that makes this equation true. And let's just put some variables in here. And note that in this case, when we're multiplying this way, A multiplied by column J of A inverse gives us column J of the identity matrix. So in reality, this is just like solving a system of equations that has two right-hand sides. Okay, so we have a system, for example, a system with one vector on the right-hand side and another vector on the right-hand side, and we need to find the values of the parameters such that both equations are solved. So we could just solve two equations at one time. And what we're detailing here is a process called Gauss-Jordan elimination. This is very similar to the Gaussian elimination process that you saw for solving the equation AX equals B. So here we're going to solve the equation with column 1 of the inverse, and that's going to give us column 1 of the identity matrix, and we also have to solve the equation with column 2. And that will give us column 2 of the identity. So what we can do here is we can augment our A matrix with the identity matrix, and I can start to do elimination. And I'm going to do elimination steps until I get the identity matrix on the left-hand side. So let's just start to go through this. This, of course, is A. Over here I have I. And first I'll eliminate the 2 using this pivot. I will eliminate the 2. And if I do that, my second row looks like that. I'll do the same thing on the other side. And this, of course, is row 2 minus 2 row 1. My next elimination step, I'll use this pivot to eliminate the 3 above it so that I can get an identity matrix on the left-hand side. So this elimination step was row 1 minus 3 times row 2. Okay, so A inverse is equal to the matrix 7 minus 3 minus 2 and 1. So how can we see that this works? Well, we're starting with something like this, A and I. We begin to do elimination steps. So we can think about these elimination steps as matrix multiplications. Say EIJ. So each elimination step is an EIJ, and then the product of these elimination steps is E. Just like we did with Gaussian elimination. So we can say E times the matrix that we start with. Well, this multiplication is clearly going to give us I, because the steps that we used to form E took A to I. And then so the question is, what goes here? Well, since EA is equal to I, E equals A inverse. Therefore, E times I is equal to A inverse times I, which is equal to A inverse. So what goes here? A inverse. Okay, so it's pretty easy to see that this process works. What happens if we want to find the inverse of a product of two matrices? So suppose we have two matrices, A and B, and they're both invertible. And we can ask the question, what is the inverse of A times B? So we want to find something that we can multiply times AB so that the result is the identity matrix. Well, if you think about this for a minute, suppose we multiply AB by the product B inverse A inverse. Well, remember that I can change the parentheses around as long as I don't change the order of the matrices. So I can write this, and that of course equals A times I times A inverse, which equals A times A inverse, which equals I. So the inverse of the product AB is B inverse A inverse. And we could extend this same idea to products of 3, 4, or more matrices. What about if we took the transpose of A? So suppose A is square, non-singular, or invertible. And we can say, what is the inverse of A transpose? Well, in order to figure this out, I need to be able to reverse the order of the multiplication. So I know that A times A inverse is equal to I, the identity matrix. And now if I take the transpose of both sides, I will reverse the order of the multiplication. I can reverse the order of the multiplication. So A inverse transpose times A transpose would be equal to the identity matrix transposed, which is equal to the identity matrix. So A inverse transpose is the inverse of A transpose. And we also see from this that inverting and transposing can be done in any order. Okay. So we have this idea of Gaussian elimination, which gives us the solution to AX equals B, and also allows us to find the elimination matrix so that we can find the equation EA equals U. And now we have the idea of a matrix inverse. So we can combine these ideas together and find a factorization of A, find the equation A is equal to LU. So we go from A to U using elimination. And we can ask, what is the connection between A and U? Okay, so let's look at a matrix A. Suppose we have A equal to the matrix 2, 1, 8, and 7. And we can do elimination on this matrix, and if we did, we would find that E21 is equal to 1, 0 minus 4 and 1. And so E21 times A would give us the result of our first elimination step, which would be 2, 1, 0, and 3. And now we have a matrix that is in the upper triangular form, and we have the equation E A is equal to U. We only have one elimination matrix, E21 here, so E is equal to E21, and EA equals U. Now, suppose we want the equation A equal to LU. Okay, so in this case, we have A, 2, 1, 8, and 7 equal to some matrix L times U, which in this case was 2, 1, 0, 3. Well, we have the equation already, EA equals U. If we multiply on both sides by E inverse, we get the following. A, multiply on the left-hand side here, so I have E inverse E times A equal to E inverse U. This gives me an identity, and I get A is equal to E inverse U. So this connection between A and U is the inverse of the E matrix. In other words, L is equal to E inverse. In this case, E inverse is equal to the matrix 1, 0, 4, 1. And so we can write the equation A equals LU. Okay. Now the L in this case stands for lower diagonal. We see that L is a lower diagonal matrix, U is an upper diagonal matrix. We can also write this equation, L multiplied by our pivots multiplied by this matrix U, where we factored the pivots out. Okay, so let's imagine now that we had a 3 by 3A. So our first step is to multiply on the left, or pre-multiply by E21. Second step, pre-multiply by E31. And our third step and final step is to pre-multiply by E32. So this gives us the equation E32 times E31 times E21 times A is equal to U. Now the question is, how do we move all the E matrices to the right-hand side? To find A is equal to sum product times U. And we should note that each of these E matrices is very easy to invert. We have to reverse the order of the E matrices. And we get the following. And this, of course, is equal to LU. And this product that we see here, E21 inverse times E31 inverse times E32 inverse, is actually going to be nicer than the product E32 times E31 times E21. Why is this? Well, suppose a typical case that we would see, we had the following. Suppose this one was E32. And this one is E21. And in this case, just suppose we didn't need an E21 or E31. Suppose E31 is the identity. And this would happen if, when we do the elimination of the 2-1 position, we already have a 0 in the 3-1 position. Okay, well, if we take this product, this is what we get. And we can ask, well, how did the 10 get there? You see, all the other numbers that are in this product are numbers that we use during the elimination. So for example, when we eliminated the 2-1 position, we took 1 row 2 and negative 2 row 1s, and we see that those numbers remain in the E matrix. And when we did E32, we took negative 5 row 2s and 1 row 3, and we see those numbers remain in the E matrix. But the 10 was not part, we never used a 10 during an elimination step. But because we subtracted 2 row 1 from row 2 and then subtracted 5 of the new row 2 from row 3, we ended up with a 10 there. So when we do it in the order let's just say it got there because we subtracted twice row 1 from row 3, and then we subtracted 5 of the new row 2, from row 3. So the 5 times the 2 is what's giving us the 10. So doing it in that order, row 1 affects row 3. Okay, the first row affects the third. Because ultimately 10 times row 1 in this case was subtracted from row 3. Now, suppose we do it the other way. Suppose we use the inverses. So we want to do the equation. Remember, we have to reverse the order. E21 inverse times E32 inverse. Okay, well first we have to find the inverse of these matrices, but that's not very hard. You'll see the pattern emerge here. There's E21 inverse. Okay, so let's just look back at this point. Here's E32. Okay, this is an identity row. This is an identity row. Here we have 0, minus 5, 1. Now to invert it, we just take, since it's only that one row, we need to just get rid of that 5 there. We just take the opposite. And here's E21. Again, an identity row at the top, an identity row at the bottom, and then minus 2, 1, 0 in the middle. And so we're just negating the 2 and that gives us the inverse. So there's a pattern. It's very easy to find the inverses of elimination matrices. Okay, so let's look at this product. This product is equal to, of course, it's equal to L. And in this case, it's going to be 1, 0, 0, 2, 1, 0, 0, 5, and 1. All of these numbers are numbers that were used in the elimination. In this case, the order of the matrices that form L is the right order in the sense that the multipliers that are in the matrix L are left unchanged. Okay. Now, of course, all this assumes that we didn't have to do any row exchanges during elimination. Okay. Let's look at a 3x3 example. Okay, so suppose we have a matrix such as this one, and we want to do LU decomposition. Okay, we'll find the LU decomposition. Okay, so we do our row operations. First one, row 2, is going to go to row 2 minus 2 row 1, and the second one is going to be row 3 will go to row 3 plus 3 row 1, and that will give us that'll give us this matrix, and then our final operation will be row 3 goes to row 3 plus row 2, and that will give us okay, and this is our upper triangular matrix U. Now let's look at the corresponding elimination matrices. E21 okay, so we have E21, so therefore inverse looks like this. Okay, and then we have E31. And its inverse. Like that. And finally, we have E32, which looked like this. And its inverse. Oh, this is inverse. E32 inverse looks like this. Okay, so now we can find L, which is going to be equal to E21 inverse times E31 inverse times E32 inverse, which is equal to this matrix, which is equal to L. Now, of course, you could have just multiplied E32 times E31 times E21 and taken the inverse of that, but you see that it's much easier to do it this way because you don't really have to go through any tough calculations to find the inverse of these individual elimination matrices. So probably a good question to ask at this point is, why would we want to do this LU factorization, or what are the applications? So let's talk about some of the applications. The idea of LU factorization was introduced by a mathematician named Alan Turing, and really this the applications for LU factorization come down to algorithms that you would use to solve these types of linear algebra problems in a computer. So one application is the solution to the equation AX equals B. So here, of course, we want to solve the equation for X. A and B are given. And if we have the LU decomposition, So we've used the Gaussian elimination algorithm to find A equals LU. Then we can write the equation LU times X is equal to B. And first we can solve Ly equals B, which is very easy because it's a simple back propagation because we have a lower triangular matrix. And then we solve Ux equal to Y. And this gives us the solution to AX equals B. And this is the preferred algorithm for solving AX equals B because computationally it's more efficient. Second application can be finding a matrix inverse. So if we have the equation AX equals LUX equals B, we can use the same algorithm that we just used to solve each column of the matrix X. So if we make B the identity matrix, let's make it a capital B since it's going to be a matrix. And then we can use the previous algorithm to solve for X, which is A inverse. There's also applications to computing the determinant, which I won't go into now because we haven't talked about determinants yet. So LU decomposition has applications for computational mathematics. It's an efficient algorithm for solving matrix inverse problems as well as solving AX equals B.